So, good afternoon for everyone. At first, I would like to thank the invitation of Professor Mauricio Garrione. It's a great pleasure to me to be here. And yeah, it's very nice. It's my first time in Milan. So it's really nice to have this opportunity to talk a little about my field here about this type of this type of equations, functional differential equations. So thank you very much, Maurice, also for the introduction. And yeah, today I will talk about a little of these equations, the functional differential equations, and I will try also describe about the averaging principle and stability for these specific type of equations. So since I realized that many people here do not work with this type of equations, I will try to start from the beginning in order to give a good introduction, and then I will talk about these two different types of results. So the outline of my talk, I will start with some preliminaries, and then I will talk about the averaging principle and the stability when we deal with these types of equations. So the main references here for this type of equations are these books. So here we have these famous books about Jackie Hale and Lunel. So this is very nice book. Also, we have these two different here that also serves for the undergraduate students, this introduction and also applied delayed differential equations. This one is very nice because there are a lot of applications concerning this type of equations. I will also comment about some models that can be described using delayed differential equations, but here it's very nice because you can find several different types of models of delayed differential equations. And also here, this another book from Jackie Hale about these equations. So I think these are like the basis for the ones that are interested about this type of equations here. So let's go to some introduction about delayed differential equations. And let's see how it looks like, the different types of equations that we have when we deal with these differential equations with delays. So we can have many different types of delays. So here what we have is like called discrete delays, that here this minus tau is exactly the delay here. And here is like a constant delays in this case. So we call that one like discrete delays when you have in this way here. But also we can have a much more complex types of delays like time and state dependent delays, which means that now your tau, your delay, is not more constant, but is a function that depends on time and also can depend on the state. So when it only depends on the state, it's called state dependent delays. When it's depending only the time, it's time dependent delays, but also it can depend on both and the time and state dependent delays, like in this case here. Also, we have another class of equations that are much more complicated to deal. That's called neutral equations. And what that means, this neutral. Neutral only means that in the part that you have the delay, you also have the derivative. So here you have the derivative in the part that includes delay. Of course, you can also have another one without the derivative, but always when you have the derivative together with the delay, we call this type of equations as neutral type of equations. So this is a type of neutral equations, but here with discrete delays. And when I talk about the stability, I will explain why this type of equations are so complicated to deal, the neutral, especially if you think about stability using linearized equations. So using linearization, we have a lot of problems when we deal with the neutral equations because of the complexity of the spectrum that appears from the linearization in the semigroup. So we have that the spectrum of the generated semigroup is very complicated. And here we have some complicated things when you deal with neutral. That's because of this derivative here. Also, we can have the distributed delays. So we have two types. So many people nowadays works with this type of delays that appears in the integral here. So if you see the delays here in the integral, and when it happens, we call it that distributed delay. So it happens in many models. Also, for example, depending on how your function f sees, for example, you could have here some kernel also, and then doing some change of variables, you could also have this type of a distributed delays. So it appears in many also examples. Also here we can have distributed delays, but for infinite delays. So here in that case, here you can see a type of kernel here. And then what we have is like infinite delays, and it brings much more complexity when we deal with infinite delays because of the phase space that we need to deal when we work with this type of delays. I will also explain a little more about that, but only to show that these delays, that the memory effect can appear in many different types. So, for example, also people that work with a fractional, if you see the fractional also brings some memory, because usually you can write the fractional depending, okay, in the sense that's what are you thinking, for example, Himmelville or Caputo, but you can write an integral form using the kernel, and this kernel also, again, you have this memory effect. But sometimes the memory is associated by the material when you deal with a fractional, but also it can deal with other types of memory about this fractional. That this is a type of a delay, let's say. So here again, we also have this type of distributed delays that appears. And usually like Volterra integral equations always have something like that, that also again, we can have this delay in that form. So here we have implicit delay equations because sometimes we also want such a type of inverse problems. It also is very common when you deal with delays that we would like to find out some delay that can optimize something. So it's also very important to have the opposite way. So here we have such a type of implicit delay equation that the delay is somehow implicit in the equation. So we also can work in this way. So here you saw a lot of types of equations with delays. Of course, we can combine many different types like neutral types with state-dependent delays, neutral types of time-dependent delays. So we can have several different types of equations, of course, depending on your model and what you'd like to describe. And that's what's very interesting in this situation. The only problem is about the difficulties behind of this type of equation. So let's see how this field was born, the birth of these fields, and about the history concerning the models and why to put delay inside of certain models. So first, when we try to think about the history of the delay equations, we have that the first works that we had in the past comes from Marquis de Condorcet. He was one of the first to investigate some partial differential equations, but then in that moment with partial differential equations, he was one of the first to arrive in some delayed differential equations. So it was the first techniques that appears about delayed differential equations. So working with PDEs. Also, we have that Poisson working with other types of PDEs arrived in some certain types of delayed differential equations. So there, in that moment, appeared the first techniques to solve this type of problem. Just to mention, since there are a lot of people here from PDEs, it's also there is a relation between PDEs and the delayed differential equations. So some PDEs can be written as delayed differential equations. And using this connection, we can investigate it about PDEs using delayed differential equations. So this is very nice, and it appears here exactly in that way. So you can also like here write your equation and try to translate it as a delay differential equation. Sometimes it's possible, sometimes not. But here, what happens is exactly that. So studying other types of problems, he arrived in a delay differential equation. So, but okay, so maybe you're thinking, okay, but they were in that field like not because they saw that delay differential equations are so nice, but because they were investigating about PDEs. But now I will bring some motivation why to investigate it, delay differential equations. So, in order to do that, one of the first that we need to sit here is Vitor Volterra. Vitor Volterra realized that usually when you deal with biological phenomena, you need to consider the time, the influence of the past in the present moment. So we know a lot that the past influences a lot what will happen in the future. So it's really important to take into account. So we know that many phenomena in the environment, uh, it's not instantaneously, but there is one time in between the action and also the future. Let's say, for example, everything that you can think, you need this time. For example, pregnancy, also concerning you take some medicine, so there is some time to start doing some effect. So all these times you can they can be viewed as a delay in your equations. So Vitor Volterra realized the importance of these delays in all biological phenomena. Also, we have that Charles Picard was the plenary speaker at ICM in 1908. And in his plenary talk, he mentioned about the importance to deal with delay differential equations when you want to describe some phenomena. So, explaining the importance to considering those delays in the description of any phenomena in biological phenomena specifically, because you need this time in between. Also, he mentioned about the difficulties in order to have to deal with this type of equations. There is one paper from Jackie Hale that he brings this part of the lecture of Charles Picard. That's very nice. The name of this chapter that Jackie Hale wrote is History of the Delay Equation. So let's see a little about some how it can be viewed in a model. So very simple here. Everybody knows a lot about the population models. And when we think about population models, okay, the first one that comes to our mind is from Verlush that brought the logistic equation that's very famous. And after that, we have that Hudson was one of the first to think that, okay, the logistic equation is very nice. However, it does not consider the time in between the birth and the enter in the maturation process. So you need to have this time in between. For example, when you have a baby, the baby cannot reproduce. You need a certain time in order to reach some age or some stage in order to be able to reproduce. So this needs to be in your equation. And then Hudson um, decided to change the logistic equation model in order to put the delay effect. So here you can see it's very, very close to what we had for the logistic equation with the difference of this tau here. So this tau here is exactly the delay. So maybe you are looking at it and say, okay, but okay, he only put this delay, the constant delay, the C plus 1, let's say. And okay, but probably it will not change very much the behavior of the solution. But here it's important to emphasize that this very small delay, constant delay, it can change a lot the behavior of the solution. And here only to show to you what happens. So here we have the behavior of the solution of the logistic equation, and here is the behavior of the Hudson equation. So that small delay that we put in our equation, that constant, we can see that it causes a lot of oscillation. So it's really important to considering to insert in your equation the delay, because the delay can change everything. And maybe you are thinking, okay, but the population models with that, how it looks like, it seems strange. However, if you see there are a lot of populations that really has this oscillation in the behavior. For example, this equation of Hudson equation, the population model was very famous about the blowfly populations, because in that time there was a lot of blowfly, and it was getting a lot of problems with the agriculture, also with some money that they would like to produce more things, and because of the increase of the blowfly population, they were really concerned about that. And the best way to describe this blowfly population was introducing delays. So because they had exactly this very oscillatory behavior. So we can find many population that really has this type of behavior. So, and here another one that we can see, like lemmings. Also, we have this oscillation type of behavior. Also, this other one, we have this type of oscillatory behavior. So, but Nixon realized one problem in the Hudson model, because if you really look into it, so let's back very fast here. If you really look at the Hudson model, what happens is that here this B is positive and also this K is positive. And if you do here the multiplication, what will you see is that the delay appears in the negative part. And this is referred to the death rate and not the birth rate. And if you're considering the meaning of the delay, that is the time in between birth and entering the maturation process, so it should be in the positive part and not in the negative part. But then Nixon realized that, and also these three researchers, Paris, Malt, and Coutinho, they realized that it was not so good, the model, doing some experiments with a blowfly. So they started to do some experiments with a blowfly population, and they realized that something was wrong in the model. Then they brought this model that is very well known as blowfly equation. And here we have this delay. So in the positive part, and now in the negative part, we do not have the delay. And again, we can see that it continues with very highly oscillating behavior. Even if we change the part of the delay, of course, we have different types of oscillations, but again, we have oscillations. So here in the first one is if you consider your delay equal to, and here in the second one, if you consider your delay equal 6. So you can see that, again, it's oscillatory the same way as before, but of course, a little different, the form that the oscillatory behavior is taking. Okay, but later, some researchers realized that, okay, very nice that we needed to consider the time in between the birth and entering the maturation process. However, it's important to mention that not always species will have the same time in between birth and entering the maturation process. So it maybe will change and will depend on other factors. And they realize this with some whale and seal populations, that this time in between could change depending, for example, about the food and other factors. And here they consider state-dependent delays in the model. So the model that they consider now, it's with this tau here, and the tau is no longer constant, but now it depends on the state. So here we have a state-dependent delay model. It's the same as we had before. If you do some change of variables, you can arrive in a type of logistic equation. However, here the state-dependent delays, it's not constant anymore. You have this different type. Now is a function that depends on x. So here it's published in this paper. And again, here we can see the oscillatory behavior of the state-dependent delays if you consider the state-dependent delays in this set. So again, this oscillatory behavior continues. And here, one question that someone can ask, for example, it's so hard sometimes to deal with state-dependent delays. I will also explain that. And one question that could come is that, okay, can I work with, for example, constant delays and do some approach and maybe the error is not so big? Here in that case, specifically, yes, this is true. If you see here, constant delays equal 40, it's very close to the behavior of the state-dependent delays if you're considering this interval here. However, it's not true always. So it also can be different. So sometimes you can have, for example, that the solution is stable for constant delays. And then when you do like a state-dependent delays, you can have instability. The same can happen for time-dependent delays. So it's not always true that you can have the same type of stability. So here it's really important to mention that these mathematicians with others realized that always in population dynamics, it's very important to consider state-dependent delays, not only constant delays, but state-dependent delays, because it really changes a lot the dynamics and also the solution. And it's really important if you'd like to have a more precise model. So now that probably you are very motivated with delay equations, I will try to bring more about the difficulties in order to deal with this type of equation. So here is how it looks like. So the equation. So I will only explaining the meaning because I know that a lot of people here works with partial differential equations and look for that and think that this is exactly the partial one, but it's not. So here we are dealing only one variable. So x is only one variable function. So here this means everybody can read it or no? So from here, okay. So here, this means the following. So here, if we considering like finite delays like that, so what we have here is like a function that takes theta here and brings to this t plus theta. So this is what we have. So this x of t theta is equal to this one. So here what we have is that now this part here is a function. So when you deal, for example, with ODEs, usually you can have like say this and this is something Rn, but now we are dealing with the space of functions. And this brings some difficulties because you are dealing with infinite dimensional spaces, and then you lose a lot of properties. And here, the initial condition that we have is also a function. So that means that there is some theta here that's equal this phi theta for theta that belongs to minus r0. So again, what we have is that d is defined by x0 plus theta. So again, we have that the initial condition is a function, not only in a point what's happening, but you really need to know what's happening in an interval. And this brings some difficulties, including if you try to do some simulations, because when you do some simulations, what happens here is that you know what's happening with the solution in the beginning, and with this information, you know what will happen in the other interval. And then with this information, you know what's happening in another interval and so on. And it's different when you deal with like ODEs that you only need to know the initial condition, and you can calculate the solution in any time. And so it's completely different. So because you need to iterate several times when you deal with simulations. So so here we have a lot of difference in that case. So here, like a ODE, you have in some moment you have the initial condition, and also in some moment t you have x of t. But when you deal with functional differential equations, we have some problems here, because here we have some initial function, that's your initial condition, and sometimes, depending how it is in that point, you can have like some discontinuity depending how is your solution. So it's really complicated. You really need to deal with that and work. You lose a lot of smoothness in some parts because of this. Uh, since you know the solution here, and then you need to calculate what's happening in the other parts. So here again, when you talk about x of t, like that, you are dealing with functions and not no longer with vectors. So this also brings a lot of complexity. So here, only to mention that, of course, we can have much more types of equations like time-dependent delays, state-dependent delays, and also the neutral type. So again, here the same, but now with the derivative here, and also, okay, this one we saw before, it's with constant delays and also time-dependent delays and state-dependent delays. So we can have all of them in that case. So let's see a little about some possible applications of this type of equations. So the first one that we have is about the neural networks. So these authors, they realized the importance that you really have when you deal with neural networks, because when you send some information, this information takes time to processing, and this time can be viewed as a delay. And so that we are dealing with artificial intelligence that is somehow processing data, it's really important to think about delay. And here, for example, this is a very recent paper that brings about the processing data. And here is the user, and the user is sending some information to the server processing. And for example, if you open in your computer several things like Microsoft Word, also Adobe, and also on the Firefox, and if you'd like to be very fast and open many, many things, your computer will be more slow. And this is because this delay to processing everything will depend on the quantity of things that you are giving to your computer to processing. So this is exactly what they try to show with that. So users send some information to some line here. So here are several information that are sending. And the server will take longer and longer, depend on this queue that we have to processing it. So this is a type of state-dependent delay. So the delay will depend on the state, on the quantity of information that you give. So here, it was the paper that they published these results about state-dependent delays for processing data. Also, the medicine, there are huge references concerning take medicine, and we know that it takes time in between take the medicine and be okay. Yeah, we know that, for example, if you have a headache and you try to take the medicine, and if you'd like to be okay very fast, you can't, because you really need the time, and this time is the delay. There are huge literature and models concerning this time in between, especially in some medicine that we don't know if we can take it periodically or not. Like, for example, people that have diabetes, you need to see the concentration of insulin in your body. Also, proliferation of cancer cells. Again, we know that the proliferation is not instantaneously, but it takes time. And usually we have, in this case, PDEs together with delays, because exactly it takes time and it depends on the stage of your cancer. So again, it's a type of a state-dependent delay. Also, we had COVID-19, yeah, and we saw that one person was infected and the symptoms does not appear like instantaneously, but there is a time in between being infected and the symptoms appears. And this time can be viewed as a delay. There are several types of models about COVID-19 using delays. And the waves that we saw, the oscillatory behavior, of the contagious was also can be viewed as a delay. Also, Zika in Brazil, we have, and this again, we have this incubation period about the virus, and exactly this can be viewed as a delay. Zika is transmitted by a mosquito in Brazil, and we not only in Brazil, in the countries there nearby. So we have this the mosquito, the same as dengue, and it's very important to consider this timing between the incubation period. The same for dengue. There are a lot of people working on that in mathematical biology, people working in University of Miami. They are doing some models with delays to describe the contagions of dengue, and also Zika is possible. Okay, so I talked very much about this only to bring you some inspiration about the delay equations. And now I will try to briefly talk about some problems that we were working in the direction of these fields. So one of them is averaging principle. So I will try to explain very briefly what averaging principle means. So when you try to understand better about the three-body problems, so if we come back to the past, to the Poincaré, and when you try to solve this type of three-body problems, to see how the influence of the third body can be in the others, you really need to like it's so hard to solve directly the problem, and sometimes it's very important to try some approximation, and averaging principles bring in that direction. So here what's happening, so here we have here the original equation. So a model of this, it's a non-linear type of equation here, so if you see, and here we have these parameters, and here is like a low d, very simple. And if your function f is t periodic in the second variable, so we can have the averaged principle. What that means? So if you define your f0 like that, so here is the period of your function f. So here, if you define as the averaging, so what we have is that we can construct this averaged equation that we have here. And what we know that the solution of the original equation is very close to the solution of the averaged equation. Of course, under certain conditions like boundness, Lipschitz conditions, we can approach both. And why this is nice? Because this is very easy to deal, since you have like autonomous here, you do not depend on time, and that one is a no linear, is much more complicated. And for example, you know what's happening when your time is the asymptotic behavior of your solution. When time grows, you have the solutions are closer and closer. So you know about the stability, instability of your solution using these methods. So here, just one example. So very simple. You have this original equation here, and then we know that cosine is a 2p periodic function. Then we can calculate using that formula that I showed before. So we can construct this, and then if you plot both, So you see that in red is the solution of the averaged equation, and in blue is the solution of the original equation. So we can see that both are really close from each other. Then when we pass this for the delay equation, we can have the same. Also, we can have the averaging principle for the case of a delay. And here, this is the original equation that we have. And making the same formulation, we can calculate the averaged equation. And again, we can see that they are very close from each other. So here, in red, we have the solution of the averaged equation, and in blue, we have the solution of the original equation. And it's very important to mention here that for a long time, it was completely open concerning averaged principle for state-dependent delay. And now, very recently, we were able to prove that for the periodic case. So it was something that it was completely open, and it was really important because there are several applications for people from the automatic engineer that they can do a lot of simulations with that and study stability. And we were able to prove that very recently about this approach between the averaged solution and the original one. Also, it's important to mention that it's possible to extend it not only for the case of periodicity, but also for the non-periodic function. And in this case, what we have here, we deal with this limit. So instead of t be the period here of the function, it will be the limit, and then we will calculate the f0, and then we again have that the original solution, the original equation solution will be very close to the averaged equation, the solution of the averaged equation. So here again, we can have that. For the delay equations, also it can be, we can have exactly this. But again, it's important to mention that there are some open questions. For example, for neutral case, it's completely open. There is nothing in that direction, include for the periodic case. State-dependent delays for the non-periodic case is completely open again. So we have a lot of questions in that direction concerning average principle for some equations with delays. So yeah, there are many open questions. Also, for example, for Volterra type equations, we are with open questions. So now I would like to talk a little about stability, but a very I'll not take too long. Just to mention some things that I think it's really important to understand a little about of the complexity to deal with this type of equations. So usually we have two types to attack the problem when we deal with stability. One is using linearization, and in that case, we only know about the local stability or instability. And the other one is the Lyapunov functionals. So here, okay, we can have both in that case. But when you deal with linearization, it's much more complicated because when you deal with neutral type of equations, what's happening is that when you linearize it, your problem, you can have from the linearization a semigroup that appears. But the problem is that when you will investigate about the spectrum of this semigroup, you can have in the neutral case infinite eigenvalues. And what means is that when you try to have some lower bound for your semigroup, it's very hard to have that because you can have infinite eigenvalues. So it's really, really difficult. So we have some difficulties when you deal with a neutral type of equation. So there are several open questions also in that direction. We use, during my stay in Germany, we proved it, linearized instability principle for a class of neutral equations that comes from a model for exchange money and with state-dependent delays. But again, we needed to assume a lot of strong conditions in order to prove these results. And we would like to improve that like with better conditions because yeah, it's somehow because of these problems that we can encounter about the spectrum, we can have this type of problem. Other problem that we have here, not only about stability, but usually to have the stability, we need first to ensure the existence, uniqueness of solution, not uniqueness always, but like existence, and also the possibility of prolongation of the solution. And the one problem that we encounter is about the regularity of our problem. Because if, for example, let's say if you have here some F here, that you have T, and here you have something like that, like a state dependent delays. What's happening here is that if your X is not continuous, let's say that your X is regulated functions, which means the lateral limits exist. So if you compose X with X, so if you compose two regulated functions, the composition maybe is not a regulated function. So you cannot ensure that a composition of regulated functions is a regulated function. So also the same can happen with some of these continuous functions. So you really need to be very careful if you want to have some discontinuities here in the solution. If you have a solution that has a lot of smoothness, that would be okay. But if you'd like to work with state-dependent delays, and if your solution has discontinuity, so you really need to be careful to find an appropriate space to work with your solutions here. And the one thing that is really important to mention, again, concerning stability, is that if you are in the constant delays, you can have like a stability. And if you change it for time-dependent delay or for the state-dependent delay, you can lose completely the stability. So this is a very weird phenomenon that appeared, but something that really needs to be explored more. Understand which types of conditions we can put in order to ensure that if you have constant delays, and if it's stable here, it should be stable in the time-dependent delay, and it should be stable in the state-dependent delay. So these are some questions that we have for the moment in these stability things. And I just want to mention here that there are a lot of open problems in the field, and especially for people that worked a lot with partial differential equations. There are several things that we can try to think. For example, Lamé equation, it's possible to investigate it using delay in the equations because it makes all sense. And there are several types of models that we can insert delays because it makes a lot of sense. And also, for example, evolution equations, when you have like a Cauchy problems, like when you have the A generated in some C0 semi-group. And then also there are a lot of groups that work with this type of Cauchy problems with delay. And there are several applications in that directions. So there are a lot of open problems in that field. Also to combine fractional and delays, because fractional can be related with the memory of the material, like a viscoelasticity and so on. And the delay can be, for example, time in between some incubation periods, or time in between some cause and effect, like you can think about earthquakes, and then there is some time in order to something happens, and exactly all those times that takes longer to happen, and you need to count in your equation. It's really important to be described using delays. So a lot of PDE's problems can be viewed as a delay problem. I have some work in that direction. We worked with Lamé equations. I worked with Tofuma and Paulo Seminario. We worked in a model that was Lamé equations with a delay. And also, I saw many people that worked with Navier-Stokes equations using delays. So there are several types of PDEs that can be better described using these types of delays. So I think it's really nice and I hope that at least you'll be interested about that. And thank you very much for your attention. And before to finish, I would like only to say that we are planning here. I don't know if I can say yet, but only to mention that we are planning maybe in the 2026 to have some joint meeting Brazil, Italy, in Milano. So I hope that it really works and we can consolidate more the scientific relations between Brazil and Italy. Yeah, that's it. Thank you very much again for the invitation.